This is another nice one. So what I'm doing is I'm just picking through my favourite questions on that Parametric Equations graph sketching chapter. I just really like this, okay? Because the fact of the matter is, when I'm in the classroom, I do spend the same amount of time it takes me to do these videos as I do in class. So I could do 3 questions on the board in one lesson. This one normally takes a long time, okay? Because what inevitably happens, this doesn't change, you know, year after year after year, is, you know, students work through the question and they say, yeah, I've got the answer. And I say, why does it do that? And they're like, Or they're like, why is that happening? And they're like, They can't really explain it. So this is why I kind of go through all this stuff. Because it's a lovely looking graph, but, you know, it's nice to see why it's happening. Right, Cartesian equation again, okay? This one is going to be a little bit tricky, because when I make t the subject there, I'm going to have t is equal to positive or negative root x. And I'm going to substitute that in. So y equals 2, that's the subtract. So subtract plus root x. And then here, that is positive, negative root x plus 3. Yeah, it's tricky, isn't it? That's the Cartesian equation though. You can't deal without the plus minus, you've got to have it. Okay. In that order as well. So when that is negative, that is positive, and that's positive, that is negative. It's a fascinating situation. I think it's kind of nice. One of the reasons why I like this question. I find it challenging. Okay. The challenging ones are the best. Okay. Right. Let's go for the obvious, shall we? So let's look to see when y equals 0, and this is nicely factorised, you'll notice. Okay, this is nicely factorised. So I hope you'll agree with me that when x is 4, in this bracket you'd have 2 minus 2, so that's fine, okay? And there's no other value of x that will make this bracket 0, is there? So it's just x is 4. And in this bracket, when x is 9, okay, you have the negative situation, the negative root x. So we'll come to the plus or minus bit later. For the moment, we just want what the x-intercepts are going to be. Okay, so you have 9 there. Okay, right, and that's it. Those are the only x-intercepts. Okay, so I'm just going to write that somewhere up here. Okay, so 4, 0, and 9, 0. Okay. I can see from this graph there's going to be a y-intercept as well. On the previous one, because it was x is 0, y is 0, that was easy, but this one, I'm going to just put in what x 0 give us. So it's quite easy, isn't it? So when x is 0, you're going to have 2 times by 3, 6. Okay, so that gives us something to start with. Okay, right, so on our graph that we plot, let's just do it here. Okay, we'd have 0, 6. We just got that for the moment, and what it's doing, we don't know. It could be doing that for all we know. It's not, but it could be. Okay. Anyway, what do we do next? I think, no, not I think, I know. We're going to use calculus again, aren't we? Let's use calculus again. Okay, let's use calculus again, shall we? Right. I don't really want to use calculus on that bit. Okay, I want to expand the brackets. Okay, to do so, I'm going to bring this one back down. Okay, expand those first of all. So what's that going to be? That's going to be 6 plus 3t. Hang on, no, subtract 3t plus 2t. Yeah, so subtract t. Let's just check that again. Subtract 3t plus 2t. Yeah, and then subtract t squared. Yeah, and then when I put, I'll tell you what, I'm going to do it parametrically. Stand by, so the first time I'm doing it parametrically. Usually I've done it Cartesian way, but I'm going to do it parametrically just to see what happens. Okay, so dy dt is equal to -1 subtract 2t, dx dt, at the top there is equal to 2t, so dy dx is equal to negative of 1 plus 2t over 2t. Yeah. Yeah. You agree with that? So dy dt over dx dt. Okay. And let's put the negative in front there. That is equal to 0. Of course, when 1 plus 2t on the top is equal to 0. So 2t negative 1t equals negative half. Okay. So what's the x value going to be? So the x coordinate is going to be t squared, which is 1/4. And the y value is going to be 2 subtract negative half, so 2 plus a half. Yeah, so it's 2.5, it's 5 over 2. Multiplied by, it's going to be 5 over 2 squared, isn't it? Yeah. Which is 25 over 4. Yeah, great. Yeah, that's right. Okay. So how do I know it's right? Because I do this question once per year. This is the first year I've actually done it in class. And when you do a particular question that you enjoy so much once per year, you get to recall the numbers. Okay, and I recall, yeah, that's right. Yeah, that's right. I don't even need to check that. I'm positive that's absolutely correct. Okay. So what does that mean? That means there's a stationary point there. 1/4, 25 over 4. So let's just do a quick sketch of this, shall we? What have I got? I've got 4, 0, got 9, 0, got 0, 6. Well, that's a terrible y-axis, isn't it? There we go. Let's just extend that a bit better. So that's 6. Now the thing with 25 over 4 is that is 6.25, isn't it? And 1/4 is there. So what I'm saying is at that point, I've just worked out 1/4, 6.25 is about there. I think we can deduce that that is a maximum point. Yeah. Then what's it going to do? Is it going to do that? All I know really is that that is going to be a maximum point. And it's clearly going to, yeah, go to there, isn't it? Okay. What's it doing there? What's it doing there? I can use some of the work on the board to help me out. Okay. I reckon it's going to do this. I reckon the y-axis is going to be a tangent at that point there. So it's not necessarily a y-intercept. Intercept implies it passes through the y-axis. It's a y touching point. Okay. Yeah. All right. So how do I know that then? Well, the thing is, when x is 0, t is 0. Yeah. And what happens when t is 0? Okay. Y is 6. But the gradient here, look at that. When t is 0, what happens to the gradient? Comes infinite, doesn't it? Okay. Comes infinite. That's effectively a vertical line. Okay. So that's how I know that this bit, let's just draw it in a bit better. Okay. It's going to be vertical at that point there. And it's going to be a maximum point there. It's kind of interesting. Now I'm thinking, right, I'm thinking the graph is going to do this. How do I know it's going to do that? Okay. Let's just mark in the maximum point there of 1/4, 25 over 4. And that's because this is kind of my finish of the graph sketch. How do I know it's going to do that? Okay. Well, I've already worked out that there's not going to be any more stationary points. Can you see that all right? Yeah, of course you can. Okay. I've already worked out there's not going to be any more stationary points. If there were to be more stationary points, you'd find some more values of t, and there aren't any. Okay. So that's it. If there are no more stationary points, you're not going to have any more minimums or maximums going on anywhere down the curve. Okay, that's the only one. All right. I can't see that x is going to be negative anywhere. Okay, because of this. Yeah. If x was negative, that would imply that t squared was negative. And we don't have complex numbers, of course, with any of these graphs. And this is not Argand diagram, it's just Cartesian plane. So the graph is just going to be this side, okay? And we know that it crosses through there and there. The only thing that's left to do is just to try and explain away what's going on. They look like they're parallel lines, aren't they? Okay, they look like they're parallel lines, and they kind of are. Let's just try and explain that one away. Why? So this is the question I ask in class. You see, when a student sketches something that looks like that, I might say, why are those two lines looking like they're parallel? And it's like, don't know. And I might say, is there a maximum point somewhere there? And they'll say, yeah, of course there is. I'll say, where is it? And they'll be like, I don't know. What's happening there where it touches the y-axis? Don't see. None of these questions I know. And the nice thing about all of this, okay, is it helps to explain our answers. And this is what I don't like, tables of values, you see. Table of values, it's kind of, takes the fun out of it. Okay, it really does take the fun out of doing it. Okay, it's like I wouldn't say a shortcut, but it's just not as nice as it. What we've got to do, of course, is see what happens as x tends towards infinity. So that's what we're doing, isn't it? Okay, as x tends towards infinity, that's how we determine the long-term behaviour. And that's an important word in mathematics, long-term behaviour of the graph. Let's just put that lovely looking curve down there. Okay, what happens when x tends towards infinity? Well, I'm going to use this equation to have a look at that. When x tends towards infinity, you can ignore the 2 and the 3. Okay, so you've got negative positive root x, okay, put that in brackets, multiplied by a positive negative root x. Okay, which means you've got either negative root x times positive root x, which is negative x, or you've got positive root x times negative root x, which is the same. Alright, so what we're saying is, as x tends towards infinity, y tends towards negative x. Okay. What does the graph of y equals negative x looks like? It looks like this, doesn't it? So what we're saying is that as x gets larger, the graph will look like this. So that kind of explains that line. Eventually that's kind of a gradient of -1, that line. Okay, just not badly drawn actually, is it? Okay. Now the thing is, because you've got part of the graph from there and part of the graph from there, okay, if both these bits tend towards a gradient of -1, they're never ever going to meet, okay, because they're both going to have the same gradient, okay, they're never ever going to meet, okay, and that's why the graph will look like that. That was quite nice, I thought. All right, hope you enjoyed that as well.